Hello, good evening, everyone. So, my name is Miguel Garcia Garibay. I'm the Dean of the Division of Physical Sciences. I also serve as the Senior Dean of the College of Letters and Sciences. And it is my absolute pleasure to welcome all of you here today. I have to say that in my role as Dean of Physical Sciences, I have the opportunity to interact with all of the departments in the Division of Physical Sciences, which of course includes the Department of Chemistry and Biochemistry, which is hosting today's lecture. But we also have some amazing other departments in the division. I'll remind you, those are the Departments of Atmospheric and Oceanic Sciences, the Department of Earth, Planetary and Space Sciences. We have the Department of Mathematics, Physics and Astronomy, the Department of Statistics and Data Science, and several institutes, among them the Institute of the Environment and Sustainability. So the Division of Physical Sciences, I'm not very particularly shy, but I feel is the best division in the college and one of the best units on campus. This is a division that is well known and recognized for really top-notch research in areas that really cover every aspect of the universe, right? From subatomic particles to the universe itself, with some amazing biochemistry and biology somewhere right in the middle. And chemistry that has not been explored by nature, that is being invented by human beings that are or have been in this department. I'd like to point that we have been honored to host the Mautner Memorial Lectures at UCLA every 2 years. In fact, the Mautner Lectures alternate between the Division of Physical and Life Sciences. So we're very, very pleased that this is our time, this is our turn. And this is a very special time, a very special year, because it is the Division of Physical Sciences' turn, and we are delighted to be the first to host under the lecture's new name, the Mautner Perkins Memorial Lecture. So the Mautner Perkins Memorial Lectures recognize both Leonard Mautner, from whom this lecture was established in 1983, which is, if you think about it, sort of a pioneer in terms of named lectures at UCLA, and his wife, Marguerite, who generously contributed and partnered with UCLA on this extraordinary lecture series after Leonard's passing. The Mautner Perkins Memorial Lecture seeks to provide a forum for scientific thought and to disseminate scientific discovery to the UCLA community and beyond. We very much value the opportunity to welcome and interact top scientists from around the world, some of whom happen to have made important contributions while they were here at UCLA, as is the case of today's speaker, Professor Omar Yaghi, who will always be welcome back. With this in mind, I'd like to take this opportunity to thank Kevin, Nellie, Louis Perkins, from the Mautner Perkins family, who are here with us this evening for their generosity, support, and this very special lecture, and the highest coveted Mautner Perkins Award. Please join me in thanking them. I would now like to invite Kevin Perkins to make remarks on behalf of his family and to present the 2024 Mautner Perkins Graduate Awards. Kevin is the grandson of Leonard and Marguerite, for whom this colloquium is named. Kevin, please.
Thank you very much, Dean Miguel. The Mautner Memorial Lecture Series was founded by my grandfather, Leonard, who was a scientist himself. He went to MIT and was an electrical engineer there, and he really cared deeply about the sciences and pursued a career in business after working for the military a little bit and helping develop Friend vs. Foe, which was a precursor to radar while he was there. And he also taught entrepreneurship at UCLA kind of as a way to share his knowledge. And he always believed that sharing knowledge was a very important thing. And so these lectures were designed to address scientific matters to the general public so that we could all learn a little bit from these great minds of the time. While at MIT, he was good friends with Richard Feynman. And so Richard Feynman was the first person to speak at the lecture, as was mentioned in 1983, and has been preceded by some really accomplished Nobel laureates and some others who have contributed just a tremendous amount to the sciences, which is a real source of pride for me and my family. The speakers include Eric Kandel, molecular biologist Paul Berg, chemist Ronald Hoffman, and president of the Chan Zuckerberg Biohub, Joe DeRisi, which was a recent one, just to name a few. And the goal has always been to demystify, again, the sciences to everyday people who are not necessarily experts, but also there was a second lecture typically that was designed for experts in science and students. My wife, Nellie, who's here, is actually a UCLA alum who is a doctor now, but did pre-med while she was here. And my father, Louis, were proud to most recently given a little bit more to endow the series in perpetuity so that we can continue to give more specifically to scholarship. One thing we used to do, we used to have fancy gala at the end, or not a gala, but a party at Riviera Country Club. My grandma would always say, you know, this is nice, but really let's spend the money on the scholarship. So I'm really honored just to be able to award some graduate student awards this year, and hopefully there will be more coming in the future. So now I will announce the two recipients of the awards. Please join me when you hear your name. So the first is Jessica Alejandra Nelson, is a fourth-year PhD student specializing in inorganic chemistry, working under the guidance of Alexandra Spokojnoi. Her research is focused on the site-specific vertex differentiation of B12-based boron clusters with applications ranging from battery electrolytes to therapeutics. During her undergraduate studies, she was part of the Yang Liu Research Group, where she led projects designing metal organic frameworks, or MOFs, for hydrogen storage, water purification, and serving as a heterogeneous catalyst for the degradation of chemical warfare agents, which unfortunately may be a really important thing in the future. Her passion for inorganic chemistry was sparked by pioneering work of Omar Yaghi, whose innovative research in MOFs has continually expanded the horizons of fundamental inorganic chemistry and addressed global challenges. And I always do not do a very good job. As you can tell, I'm not a scientist, so I do my best here. All right, and the second award recipient is Robert Lavroff, who obtained a BS in chemical engineering from Northwestern University, where he engaged in undergraduate research with Dr. Omar. And after that, he worked in software for 2 years prior to attending UCLA, where he joined Dr. Anastasia Alexandrova's group. As a member of his group, he develops and applies electronic structure software to treat strongly correlated solid-state systems where density functional theory is inaccurate or breaks down altogether. This includes certain metal organic frameworks, quantum materials, and heterogeneous catalysts. Rob is in his fourth year of his PhD and is co-advised by Dr. Dennis Uzvayat of Humboldt University in Berlin. Congratulations to these two graduate award recipients. Your work is a phenomenal representation of the academic excellence at UCLA, and we are honored to support you. Congratulations. Thank you.
Okay, so good evening, everybody. First of all, again, huge thanks to our donors for this tremendous opportunity to recognize, first of all, the amazing science that is happening throughout the world that we will hear about in about 2 minutes, but also recognizing some of our young talents at UCLA. As you can see, this is the future. And so congratulations, Robert and Jessica. For those of you who don't know me, my name is Alex Spaconi, and I'm currently a chair of the Chemistry and Biochemistry Department. And I'm extremely honored today to introduce our speaker, Professor Omar Yaghi, as the distinguished 2024 Mautner Perkins lecturer. Let me tell you a few words about Professor Yaghi. Omar Yaghi is a chemist and a material scientist, and he's currently at the University of California at Berkeley, where he had an illustrious career. And before that, during the 2000s, he was actually a faculty member of the Chemistry and Biochemistry Department here at UCLA. During his career, Professor Yaghi has pioneered several classes of new ultra-porous materials with very large surface areas, as well as very low densities, which make them ideally suited for numerous tasks of scientific and economic applications, such as carbon capture and harvesting water from desert air, as you will hear today. Omar has thus opened a new field of chemistry, which is called reticular chemistry, and provided the impetus for developing materials with completely fundamentally new properties. He is an elected member of the National Academy of Sciences, a German National Academy of Sciences, and he received numerous awards and honors from 24 countries, some of which include the International Wolf Prize, the King Faisal Award, and Century Prize from the Royal Society of Chemistry. And so today, Professor Yaghi will be presenting a talk focused on water harvesting from desert air. And so please join me in extending a warm welcome to Professor Yaghi.
Thank you very much, Alex. And I also want to extend many thanks for the Mautner Perkins family for endowing this lectureship, which is a great honor for me to enjoy the pleasure of talking to you about our research. I want to discuss water today and how we can harvest water from desert air. And I want to start with a picture here illustrating, this is the Hoover Dam, and this is the water level when I was a student back in 1983. And when I was a professor in 2003, and now. Okay, you can see that the level of water is going down, and the Hoover Dam is the largest dam in North America, and it supplies 16 to 17 million people with water. And so the question is, what are we going to do about that, right? Given the depletion of water, and this is due to climate change. Yesterday, part of this prestigious lectureship, I talked about CO2 capture from air and how we made the best materials for capturing CO2 from air. Today, I want to talk about how perhaps we can alleviate the water stress that is experienced on our planet. This is a map of the world, and it shows what's going to happen in the future, where a quarter of humanity will face a water crisis. I don't mean stress, I mean crisis. That means people do not have water to drink. And you can see parts of the world that you and I recognize as being watered, like part of the Midwest of the US or even Belgium, are going to become water stressed or have a water crisis because we're using more of our underground water than is being replenished. And so this is one of the biggest problems facing our planet. But just like the CO2 problem, chemists come to the rescue. We are the only scientists that know how to navigate this periodic table. Okay, you tell me what problem you have and tell me that society is standing behind solving this problem, and we will solve it. And this has always been true in society, in the progress of civilization. So the periodic table is something that chemists can navigate, and we have developed new materials based on this periodic table. Before I tell you what we have done, I just want to say that the advance of civilization has always scaled or correlated with the advance of the materials that we are able to develop and use. And this has been true since the Stone Age and the Bronze Age and so on. Okay? Cement, silicon, pharmaceuticals. What's next? What would be those new materials that are going to solve the world's most pressing problem, like climate and water? And I hope that by the end of this talk, I will convince you that it's these materials, metal organic frameworks, that are being investigated now in over 100 countries around the world, that they would address these problems. So you can see also that throughout the history of civilization is that the finer and finer manner with which we have been able to design materials has corresponded directly to advancing our civilization. Okay, so there is nothing better than being able to control matter on the atomic and molecular level. And that's what we have done with these new materials that I will discuss today. So, what was the beginning like? Back in the mid-1990s, we recognized that there is an important potential in taking metal ions and linking them with negatively charged organic units to make new materials. Everybody at the time said it can't be done because you're not going to be able to make ordered, well-defined materials, and it's going to be a mess. Okay, but it took a young student who was not accepted at the university where I was, Arizona State University. Her English was poor, and she was pushed away by the professors, and she was selling, 20 years later, she told me that she was selling flowers on the streets of Phoenix to sustain herself. But she pushed herself into my office and said, I want to join your group. And I said, no. I am a young professor. My lab is not set up. I think you need a more senior professor to do this, to plug into the research that's going on in their work and get papers and go on to develop your... So I wasn't ready to accept you. But she kept coming back. And then, of course, 20 years later, I thought, well, she joined my group because she didn't have any other option, rather than because I was a promising young professor. But nevertheless, she was the one that cracked the door open. And she was the one that showed that these things can be crystallized. And that was really the beginning of the MOF field. And then we built on that success by making materials like this that are made, you can think of them as networks. The junctions are metal oxide units linked by organics, and we use the yellow ball to indicate the space on the molecular level into which one can stuff CO2, as I showed you yesterday, but also water and other materials. But there is a story behind this discovery as well. And that is that the student that discovered this compound initially deemed it uninteresting. They looked at these crystals, they were in love with them, but they picked them out of the solution and put them on the diffractometer. And of course, they had lost their crystallinity because we didn't know they were filled with solvent because they were porous. So I was not hovering very far behind the student and said, no. You need to mount this crystal in its mother liquor or in the liquid. And that was this structure. And this structure, the reason it's so special is because it broke the surface area record of all materials for the last 1,000 years. It was so porous with a surface area of 2,900 meters square per gram. And just to give you an idea, now we are used to these high surface areas because of MOFs. My colleague at BASF, with whom I have collaborated over the last 17 years to scale up MOFs to multi-ton quantities, revealed in an article that was published in a chemistry journal that the number, that means the surface area number, was so unbelievably high, I thought it had to be a misprint. Okay, and that's how amazing that surface area was. So later, BASF, that was when I gave the first talk about that material in '99, I met BASF colleagues who then showed the world that in fact MOFs can be scaled up to multi-ton quantities. And you see this plant here where the MOF, which is like a powder, like a baby powder, in this case it's zinc, MOF is being filled into these large blue barrels. That was the start of a field. It changed the way people think about making materials because you were taking inorganic units that you find in minerals with organics, putting them together to make ordered, porous materials that had the potential of solving some big problems. But not only that, not only can you make this, but you can vary the components of them. Not only can you make this pore size, but you can make larger pore sizes by lengthening the size of this unit, the length, the functionality, and the connectivity. Everything about the structure we can vary. And we can vary the pores and the chemistry inside the pores. What I'm trying to say is that this chemistry, not only did we make this compound, but we made hundreds of these, and the community has made hundreds of thousands of these, is that if you can think it, you can make it. Okay, you imagine a structure that you want, you can make it. That's the signature of MOF chemistry. And so we opened an infinite frontier we called reticular chemistry because it brought to chemistry the domain of extended structures where inorganic and organic disciplines that are considered separate and taught separately together into one class of materials where the greatness of chemistry in terms of precision of design can be incorporated, and with hundreds of applications in clean energy, water, biotechnology, and even medicine are being pursued. We did an impossible experiment, and that was to take a crystal of that structure I just showed you to really characterize that it's truly porous. Because once you have a porous material, if there is no stuffing inside, nature abhors vacuum. If I take that stuffing out, now I have vacuum inside the crystal. So we wanted to prove that, in fact, when there was nothing in the pores, that the structure still is maintained. The reason that's important is because you want to be able to capture CO2 and take it out without the structure collapsing. And so we proved back in 2005 that beyond doubt that, in fact, an evacuated structure could be determined by single crystal X-ray, and that in fact it remains open in the absence of gas. But we also discovered that everything in a MOF is an adsorptive site, meaning that everything in a MOF could be designed to attract a gas molecule like CO2, or in those days we are working on hydrogen, the metal oxide units were adsorptive sites, parking spots, let's call them, bees on a honeycomb for gases. And the organic units were also serving as adsorptive site, both the six-membered rings and the faces of the six-membered ring and the edges. That's why they have extremely high surface area, and that's why they broke all records of porosity for the last 1,000 years, held by carbon made by the Chinese. So what have we done? We've taken a granular sand, basically, that has a low surface area, and we've exposed every atom, billions of atoms, and made them a surface onto which one can bind. And that's why your surface area, nowadays, we can achieve 7,000 meters square per gram, because we have exposed every atom in the structure, and it became an adsorptive site. And this, if your eye can see a molecule, a MOF, it will see something like this, where you have in gray the organic part and in pink the inorganic part. And everything you're looking at is a place onto which CO2, hydrogen, water, or other gases can bind. The surface area of this particular material we call MOF 200 is 6,400 meters square per gram. That's the footage of an entire football field, trapped in 1 gram of material that is no bigger than an American quota, okay? So, or American dollar, I should say. This is what the materials look like. They're crystalline, and they have, that means well-defined structures, and this is the way we can see them with our naked eye. But if I zoom in on the molecular level, you will see that they are constructed from those joints, metal oxide joints, organic linkers, to make open structures. And you can see the gases then can be stuffed inside by virtue of their attraction to the internal surface and packing them because they are attracted to the internal surface, to those surface sites that I talked about in the previous slide. So that means I can take gases that fill very large volume and compact them into small volume, and that makes hydrogen storage a potential reality. It has made CO2 a great reality, as I showed yesterday, and today I want to talk about how water harvesting from air to make drinking water becomes a reality. Well, this is the map of the world again. This is the stressed water regions of the world. Obviously, Greenland and so on are stressed because the water is frozen. But in these regions, it's a more serious problem. And the idea was that if I can make a material that takes water out of the air in these regions, it would work in the other regions of the world that are more humidified, but maybe the water is not clean. So I can deliver water in the arid regions, as well as that same material can work at higher humidity. Humidity in the arid regions is like 10%, relative humidity 20%, 30%. In these regions, it goes up to 70, 80%. But water may not be clean here, so we can use our materials. So the idea was, can we harvest water from air anywhere in the world at any time of the year? And before any of you tell me that we're going to dry the weather and you have to use a lot of lotion and moisturizing creams, there's plenty of water in the air. There's almost 13,000 cubic kilometers of water in the air at any one time. That's equivalent to how much water we have in lakes and rivers on our planet. And if I was to give each one of us on our planet 50 liters of water a day, we would have only used less than 0.001% of the water in the atmosphere. So there's plenty of water in the air. There's no need to panic about drying the air. Why is it so difficult to take water out of desert air? Let's look at a psychrometric chart. This is basically a plot of water vapor in the air in grams per cubic meter versus temperature. And I have colored the arid areas in brown and the humidified areas in green, roughly. But let's imagine that I'm in a city like Granada, Spain, okay? In the summer, I'm at 30 degrees Celsius, and the humidity is as low as 20% relative humidity. And let's say I want to take the water out of that air. I have to cool down the air down to 4 degrees Celsius in order to get to 100% humidity and be able to condense that water. Well, that's refrigeration. That's not energy efficient. But let's imagine that I have the MOF that I just showed you, and I can program it to pluck water out of the air, concentrate it in its pores, and then I take that MOF and I put it in a box, close that box, and expose it to sunlight. What's going to happen? The box will get heat up, the interior will heat up, and water will come out of the pores and condenses on the walls of the box. Now I can collect drinking water. No energy input aside from ambient sunlight. I have managed in that experiment to turn desert air into tropical air. And therefore, now I have turned arid air with relative humidity of 20% to 90% or 80%. And to get the water out of that air, I only need to cool by a few degrees Celsius. Okay? That's the idea of water harvesting. That's how the MOF works. So this is a MOF. I won't describe it, but it's a zirconium MOF. And the student came to me with this red plot and said, well, that's the behavior of this material in water. We were studying the behavior of materials in water because we were trying to trap CO2 in the presence of water. And as I showed you yesterday, CO2 capture is helped by water, but we didn't know that at the time. So we were studying how does CO2 and water behave. And so we were taking these measurements with water, and we get the red line. And when I looked at the red line, I was almost floored because it's taking up water at very low humidity, 20%, around 20% relative humidity. But what was more amazing is that you can take the water out in the green at 45 degrees Celsius. Okay? Well, that's nothing. That's sunlight, especially in the desert. So normally, in materials that take up water, like the desiccants you might have in food products and things like that, zeolites, chemists know about zeolites, they take up water from low humidity, but you have to heat them up to 300 degrees Celsius to get the water out. In fact, as a student, we used to heat those overnight to get all the water out. Well, that's not economical. But here, because of the organic and the inorganic components, you can take the water out at low humidity, at low temperature. And the nice thing was that this material cycles back and forth. You can take water in, water out. It doesn't decompose. Nothing happens to the material. But what we noticed is after the first cycle, there's a drop in capacity. That means that some of the water was staying in the pores. It wasn't coming out. And that's the beauty of working with crystalline material. That's what we have worked hard at in the last 25 years. And we found that those first water molecules that enter the pores go to the most hydrophilic sites and stay there. And because they're tightly bound by the most hydrophilic site, they don't come out. But what comes out are all the water molecules that bind to them. So in fact, these first water molecules were acting as seeds onto which water from the atmosphere was permeating through and binding through hydrogen bonds. And that's why when I showed you the red line, it looks like a cooperative mechanism by which water is binding into the pores. Well, that mechanism is absolutely essential to having a water harvesting material that operates in an efficient manner. If that was a shallow water uptake behavior, then you need a large change of pressure or temperature to get all the water out. But instead, you only need minor perturbation to take the water in and out. So the discovery here was that the first water molecule acts as a seed and never comes out of the moth. Okay? And that's why we had that little drop. So we were doing this experiment with MIT, with a professor at MIT, and when we reported the science paper, there was a lot of publicity about it. And MIT gave that professor $500,000 and said, forget about Omar, let's develop it on our own. But they miscalculated because we're the moth chemist and the material is the most important part. And so we went our own way and we built a device that has a box, basically a box of moth within a larger box. At night, this box that contains, in this experiment, contains 1 kilogram of moth. The moth I just showed you, 801. Desert air goes into the moth. Water is trapped in the pores, as I have been describing. You close the outer box and expose it to sunlight during the day. The inside heats up. Water comes out, condenses on the walls. Now I have drinking water. No energy input aside from ambient sunlight. That's what the box looked like. And my 3 heroes at the time, coming from various parts of the world, they rented a black SUV in the Bay Area and in Berkeley and drove with their device, with all the wires coming into the device and out, as you know, to measure the humidity, temperature, and all of that. And of course, I sent a letter with them that said that this white powder, this 1 kilogram of this white powder is actually a legitimate experiment and it's nothing to be suspicious about in case you are stopped by the sheriff along the way. Well, you've had, very interesting people going to this experiment. Well, they did the experiment and initially it didn't work. Okay, I called them at 2 o'clock in the morning because I had not heard from them. I had asked them to update me about the progress of the experiment. And they were all awake. And I was very suspicious that something bad has happened. And they said, Professor, we can see the water coming out of the moth, and it's like a vapor, but it never condenses. And I said, well, why not try to dig a hole into the ground and put the device there? Then it will condense because the ground is few degrees lower than the air. And in fact, well, they didn't do that because they were in Airbnb, but they went and bought from Home Depot some sand or whatever, dirt, and they put it around the device. And sure enough, they collected water. And from that experiment,
3, 2, 3, action.
and
Cheers.
Eugene drank the water. Not at my urging or anything. He surprised me with this video. Okay? The water is distilled. Okay. By the way, he is alive and well and running a startup. But we have tested, we have reported in this paper a scientific study that tested the water, metal content, organic. It's the cleanest water you will ever have because the moth is a filter, only allows water in. The pores are large enough for water to come in, and it goes through phase change. And it's very, very pure water. It doesn't taste as good as Eugene advertises because it's distilled water. So if you mineralize it, as we would mineralize our drinking water, it will taste very, very well, very good. Okay, so we reported that, and people said, well, zirconium is expensive. This moth is going to be expensive. Zirconium is $160 a kilo. Well, again, chemistry comes to the rescue. We made aluminum moth. Well, nothing is cheaper than aluminum. I mean, aluminum as a metal is inexpensive, $2 a kilo. We made a material out of that, and this material takes up water at even 10% relative humidity. Okay? It does so fast from low humidity, as well as if you really want to take the water fast, out of the pores fast, you can heat to 85 degrees C. Within a few minutes, the water is out. So my students designed another prototype. This one we learned from the old one, which was a cake of 1 kilogram of moth, that air has trouble penetrating through the entire cake of 1 kilogram. So now we made thinner layers of the moth, and they went to the Mojave Desert. By the way, I didn't mention, but that was the Arizona desert, the first experiment. This is the Mojave Desert. And there, they interfaced the module with the solar panel to allow to have enough power to for fans to push the air into the moth, and slight heating of the moth later to take the water out. But I want to point out these two panels. This is the relative humidity that they measured during the day and night. Okay, you can see the humidity can go up to 50%, but it can also go down to even less than 10% relative humidity during the day. But whether it's up or down, you are harvesting water, because the moth isotherm that I showed you tells you that, and it does work in the desert. By the way, this amount of water came from Berkeley in the original material. That's why it's here. So you should ignore that. But this is the desert experiment. Well, I told him, don't come back without a video that shows that you're harvesting water, okay? Because that's data. And so this is the water being harvested in real time from that experiment. And if you wait long enough, there's a bug that walks around the place, okay? They were really in the middle of nowhere in to do this experiment. Okay, from that experiment, they harvested 1 liter of water per kilogram of moth per day under arduous arid conditions, okay? That's that kilogram of moth is sitting there in the device, giving you 1 liter a day for years, because the moth is extremely stable and it can cycle. We have this moth has been cycling for the last 3 years and with no degradation. So we think that this moth is graded for at least 5 years or more. And at the end of the moth journey, you can separate, using acid, separate the metal from the organic and reassemble the moth in water in a zero discharge process, okay, invented by BASF. Okay, so now we're getting serious. Now the Eugene, in his startup in the Bay Area, we designed a device that's no larger than a microwave oven that allows air to go into the device. There's moth modules inside the device. It works in the same way I described, but now automated. This is electrified. You probably saw the water condensing on the edge there, but now you see it being collected at the bottom. And from this experiment, you can collect 5 liters of water. How much moth are we using? 200 grams. 200 grams of moth will give you 5 liters of water per day, every day, for at least 5 years. Okay, and this is a device, as I said, no larger than a microwave oven. So we have been going through one prototype after another, improving the placement of the moth in the device to expose it maximally to air. And we have also been looking at the energetics of the system, especially for the electrified device, to make sure, this is another one, to make sure that they are also energy efficient. This is not a very good video, but you can see, I call it the rain in a box. This is the same moth, but you can see that you can collect water, okay, more rain coming out of the moth, okay? You can see the fans here pushing air into the, designed to push air into the moth, and then you'll see the collection of the water under there. Okay, you want more water? Just use more MOF. And so my students are real heroes because they inspire the professor. We always think that we inspire the students, which is true, but very often they inspire us. And so they volunteered to take this MOF to the driest desert, Death Valley in Furnace Creek, a very beautiful place, very dry. And this device had pancakes. We designed the MOF into pancakes to maximally expose them. During the night, obviously, this it's exposed to water in the air. During the day, you close it and it heats up, and you can collect water from the Mojave Desert. Okay, so this is the device sitting there overlooking the valley, or the Furnace Creek Valley. Okay, but chemists have to dig deep into what's happening in the structure because we want more water. We want more. We are never satisfied. We want more. We want more precision in design. And so we did a crystal structure of the compound, but we also were successful in doing crystal structure of each water molecule that enters that MOF. And I'm going to show you, it's a miracle how this MOF works. If you're a water molecule floating through the pores, you will be viewing hydrophilic and hydrophobic pockets. And they are repeated throughout, billions of them throughout the material. And so I'm going to just extract one of these pores to highlight what happens. I'm going to shave it down to show the hydrophilic sites and the hydrophobic sites. The first water molecules obviously goes to the hydrophilic sites, then the hydrophobic sites are bridged through hydrogen bonding. Okay, they repel the water, but hydrogen bonding to the hydrophilic sites fills up the pores. And so this push-pull, the hydrophilic, the hydrophobic push-pull of the water is what makes the removal of water at lower temperature possible. Okay, and that's how it works. This is, we were successful in determining that. Now we know exactly where each water molecule is going. Now we can go back and say, okay, I'm happy with this MOF, but I want more water. What should I do? Well, you say, well, Professor, you can extend the linker and make larger pore. Well, that's true, but that doesn't guarantee that that MOF is going to form or is going to be stable, right? So we did that. We expanded the pores by using longer linkers to have more water. You can't expand them infinitely because after 20 angstrom, you start getting double step isotherm. That's not very efficient. So you are limited within that 20 angstrom thing. So in the end, we surgically inserted 2 carbon atoms into the linker. So this is the original MOF, and now we can, what we call LAX, long arm extension, 2 carbon atoms, and you can get 50% more water in that structure. Same structure, but just a little bit larger. It works in exactly the same way. All the adsorptive sites are exactly the same. Okay, that's what chemistry can do. Okay, and that's, you can see here, we're taking up 50% water. The material, the temperature at which you remove the water is even lower than the original MOF, and we can cycle. And this is now a material that's being commercialized in another startup. So where are we today? We are the passive water harvester, or the independent water harvester that uses no electric, just sunlight. 1 ton of MOF will give you this much water per day, 2,000 to 150 liters of water per day, no energy input aside from ambient sunlight. 1 ton of MOF electrified will give you 25,000 liters of water per day. Okay, now you can start thinking about the different uses of these devices. So in one of the startups, we already have a device now, the next generation device. It's as large as a small refrigerator, that delivers 22 liters per day at less than 0.4 kilowatt hour per liter. That's in California, that's about 3 cents, 2 cents, or to 3 cents per liter. Okay, in Texas, it's 1 cent per liter. Okay, so depending on the cost of electricity. But that's the electrified version. Okay, not bad actually, considering that you have your own water. You are water independent. Okay, and when you have the non-electrified one, you become really independent of the grid, and you can live anywhere you want. Instead of living in a condo, you will have a mansion in a ranch on the countryside, right? Because your water is available. And that's really the power of this technology. It's going to change the way we organize our urban environment. So based on at least the MOF 303, not the LAX, although LAX would take 50% more, we can harvest, this is the water that could be harvested from the Atacama Desert, the Mojave Desert, all year round. Okay, per kilogram of MOF, you can harvest in the most harshest conditions on our planet, 7 liters of water per day. And I can plot this depending on the weather conditions everywhere around the world, including Riyadh, Kabul, Baghdad, whatever. Okay, that's real. I have shown you the prototypes. I've shown you water coming out of those prototypes. And that's from chemistry. So the conclusion of this talk is that chemistry is alleviating a major societal problem, water, and furthermore, we hope that there would be water independence for everyone on our planet. So I want to thank my brilliant students who put up with me and financial support from these sources. And I want to thank you for the honor of delivering this lectureship. Thank you very much.
Questions for Professor Yaghi?
So you mentioned that MOFs can purify the water. So how can you make sure that the organic agent is not trapped in the purified water?
The MOF is very stable, so it does not leach out metals or organics, and we've tested that. Otherwise, we would be stopping the research if indeed it did leach out, because nobody wants to drink organics or metals. So it's very stable. And the reason it's stable is that the first water molecule blocks the most hydrolytically unstable site. That's the miracle of knowing your chemistry on the atomic and molecular level, right? We didn't expect this MOF to survive these conditions. This MOF 303, has been living underwater for the last 2.5 years. It's very stable. Why? Because water is a protecting group, as we say in chemistry.
I have a question about the harvester. When you say you can make 1 ton of a certain to create 200, 250 liters of water, how big is that device now that holds 1 ton of water?
If it's electrified, it probably will not be larger than this podium. Okay? The passive one will be larger. Will be, yeah, it will be like the 1,000 liter tank that you see sometimes on farms. But that will be sitting somewhere in your village delivering water, yeah, because space is not an issue.
Is there a cost associated yet with building those? If you were to say, for example, someone here wanted to buy one. I know it's so new technology.
We calculated the cost of providing this at this stage to, different countries and for the enough drinking water for a family of 4. It's like $1 a day. Yeah. It's, and that's only at this stage. But remember, the MOF is going to last 5-6 years. So, and it's made from aluminum. So the MOF is inexpensive. The device, it's off-the-shelf things, right? So I think that our models, at least for the first, if you want to go with the electrified device for the kitchen, that's for the 5 liters. That's $1 a day. Yeah. Yeah. When all things are considered.
So, yes, for one talk. So, my question that actually the previously condensed water will block the wave of the water vapor afterwards. So, if they're optimize the thickness of your molecule for the water harvesting, and what is the, if they're optimize the layer distance for the water harvesting?
That's a very, very, very clever question. The distance between the MOF and the condenser is very important, right? That's a key feature because when the water comes out of your MOF, it's going to change its temperature, and you want to hit the condenser while you're able to take advantage of the temperature change. And yes, you're pointing to a problem. We used to say, well, the chemistry is already solved and the rest is engineering. Well, it's not the rest is engineering that it's all well worked out. You really have to work it out. And the nice thing about engineering, chemical engineers, that where they are much more advanced than chemists in using models to model all of that, right? So you have to do a lot of modeling to understand this diffusion from the MOF to the condenser. Well, all of the things like how fast your air is going through, the kinetics of how fast water goes in, kinetics of how fast water comes out, and the configuration of the device that you get maximal condensation, right? So yes, these are issues that we have been solving in these devices. That's why we have many prototypes. Yeah.
So a second question is, due to the gravity or capillary force of the water, did you observe some distortion of
This MOF is slightly flexible, okay? When you put water molecules that are hydrogen bonded to the internal surface, they do distort the structure slightly, but not by much, right? It's not like there are bonds that are being stretched or anything like that. It's just slight perturbation of the structure. It's almost like slight breathing of the structure in and out, but it's not what causes the water to come out necessarily. It's not like a sponge, okay? It's only like a fraction of an angstrom of change,
So
yeah.
do you have some experimental data to show the distortion of like structure change of the mold after the water absorption?
Yes, this is all in the science paper that we published in 2021. It's all in the supplementary information. It's mentioned in the body of the paper.
Thank you for your talk. That was really interesting to hear. I was curious. My initial question was, you mentioned earlier that they're very recyclable in the sense that you can put them off into like an acid bath, for example. I was curious in more terms of a practical application of deploying these MOFs. Whether or not does the chemistry still hold within areas where maybe there's more coal-fired plants, we get a lot of acid rain, for example, and maybe some more acid in the air, or even in more urban settings that have a lot of like NOx during the day. Does that have any effect on the performance of the MOFs?
Yeah, acid rain, that's liquid, so it's not going to go in. But NOx or SOXs, they're gases. And fortunately for us, water is, and NOx and SOX have similar size, let's say, to water, but water binds stronger than those. So even if they do enter the pore, they can be kicked out very readily by the water that's coming in. So no, we have not observed in our experiments anything dealing with that. And by the way, You can always use like for dust particles and other, I know you're concerned, you can always use like an air filter like you would have in your car
Yeah, definitely.
to,
And then as a quick follow-up to the structural question, another question was, for example, in a high desert area during the winter, for example, maybe temperatures during the day can be high, but humidity can still be relatively low. Is there, when water cools and the moth gets below freezing for water, is there any effect on the freezing of water within the moth, or does that not even matter in this sort of situation? Does that, if so, does that affect the structure integrity of the
it doesn't. Temperature does not affect the structure. I mean, we do the crystal structure at liquid nitrogen temperature, and we're using it at room temperature. But yeah, the humidity in the air at low temperature is very low, right? So that's a consideration, but not many places in the world this would be needed. It's usually remote areas where nobody lives. Yeah, in Greenland or mountains of Kabul.
In the interest of time, we'll have one last question in the front there.
Can these be kind of designed like 31 flavors, for example, that you want one to capture nitrous oxide, you want one to capture carbon dioxide, you want one to capture certain kinds of noxious fumes that might come out of a lab, so you could design these, you order whatever you're looking for.
That is a very good question. Yes, this is the hallmark of reticular chemistry, is that you can have not just 15 flavors, but thousands of flavors, because you can go in, not just design the structure, but also tweak it chemically by adding chemical groups into it so that it is perfectly tailored to trap NOx, SOx. And this is not an extrapolation by me. These are papers that are published today that show that, including PFAS, anything, including pharmaceuticals that end up in our water. All of this is possible and has been demonstrated in the literature. But yes, different flavors, different shades of it can be made, have been made. And like I said, researchers in 100 countries, more than 100 countries, are investigating this. And it is the delight of chemists. It really is. That's why within the course of 25 years or so, it's become one of the largest areas of chemistry. Yeah.
All right.
Thanks for the question.
Let's thank Professor Yaghi. And I'll pass the baton to Professor Garcia-Garibay for several last words.
So, actually, I really don't have much to say. My only duty is to highlight and thank Professor Yaghi for an outstanding seminar. Thank you, Omar. It's nice to have you back. We hope that you will be coming back and visit us more often. I would also, of course, express my deep appreciation again to the Mautner Perkins family for making this event possible and for expanding, again, the impact of the Mautner Perkins gift to the department and to UCLA. And finally, to thank all of you for joining us. Please stay tuned. There is a lot of exciting things happening in the Department of Chemistry and Biochemistry, and you'll be receiving invitations to come to fantastic events like this. So thank you, and have a very nice evening, and good night.